Hello everyone. So in this segment we are going to learn about quantifier. So quantifier also is also a part of predicate logic. Now a quantifier means actually in which quantity we are going to evaluate the predicate logic. So there are two widely used quantifier. There are multiple other quantifiers also, but we are going to know about these two quantifier in this course. So we have a universal quantifier which is read as for all right, and we write it like as a upside down a. Okay, we write it down like that, and it is read as for all. So another quantifier is known as existential quantifier. So we use the reverse e. Okay, and it is read as there exist. Okay, so a propositional function can be turned into a proposition using a quantifier, and we are going to see some examples. So a universal quantifier looks like this. We read it as like for all. We write it like that for all, write it like that using a upside down a, and we read it like that for all x px. Okay, so the whole it becomes a proposition under a specific domain. All right, so we read it like that. It tells us the idea that for all x, okay, for all x px is true. Okay, it tells us that the proposition must be true, the predicate or the proposition must be true for all values of x in the domain. All right, so here this one also becomes like a proposition, means what we are saying that it becomes a proposition or it becomes a statement, means we can evaluate it with either true or false. So let's see some example. Let's see our px. Okay, px presents that x greater than 0. So our predicate looks like that px x greater than 0, and our domain is here. Our domain is the first case, domain is all integer number, and in the second case domain is all positive integer. Okay, so let's find out the statement for all x px is either true or false. So here the statement is for all x p of x. All right, our domain is all integer number, this is our predicate, and this is our quantifier. So we are saying that for all x in the domain p of x is true, or we are saying that the predicate, the proposition is true for all values of x in our domain. All right, so this statement, this becomes a statement using a quantifier. Okay, so we are going to show you how we are going to evaluate it using a true or false. All right, but it is a statement. Here we are not actually replacing x. All right, replacing x with a specific value, but we are saying that p of x is true for all values of x. Okay, and it is true in a specific domain. So here we have to have a specific domain. All right, a quantifier and the predicate. Okay, predicate means predicate logic. Predicate logic has also a variable. Okay, now let's find out in the domain. In our first case, our domain is all integer number. Okay, whether this statement is true or false. So if a domain is all integer number, we have to find out for all integer number p of x is true or false. Okay, so all integer number means integer number can be negative, 0 or positive. So we have like the negative number -3, -2, -1, 0, 1, 2, 3, like that. Okay, so for all positive integer, I mean 1, 2, 3, 4, for all values, the predicate is true. Okay, the predicate logic is true, but it's not the case that for all integer number this is not true. So we have some value like -3, -2, -1, 0. Okay, we'll find that this predicate is going to be evaluated to false. So here we can actually test that p of 3 false, p of -2 false, p of -1 false. So this is not the case that for every integer, okay, for every x in the domain of integer value p of x is true. Okay, so that means in this domain our this statement is false. Okay, so using this domain our statement is false. Now let's see in the second example, our domain is all positive integer. So our all positive integer, it is going to say that all positive integer means 1, 2, 3, 4, like that. Okay, so if the all the integer is positive integer, we can actually test all of them. Like we are going to see that p of 1 is true, p of 2 is true, p of 3 is true, and we know that as we approach, all positive integer must be greater than 0. Okay, so in this domain we can say that for every value of x in this domain our predicate is true because all values of x are greater than 0. All right, so in this domain our statement is true. All right, so let's see another quantifier. We're going to talk about the second quantifier known as existential quantifier. So we read it like that: there exist. We use the reverse e. All right, so we read it like that: there exists an x. Okay, there exists an x for which p of x is true. Also it tells us that the proposition p of x is true for some values of x in this domain. Okay, so if we have at least one value of x for which p of x is true, we can say that this statement is true. All right, so means there exists at least one value of x for which p of x is true. All right, now that one is a statement. Okay, we are going to have a specific domain, and in that specific domain if there exists a value of x for which our proposition, I mean our predicate logic is true, we say that the whole statement will be true other than false. So let's see the same example. It's actually I wrote this will be okay. So let's see, use the same example with the same predicate. Okay, and let's find out the truth value of this statement using the existential quantifier. Okay, so we have now this statement. Now this is our statement. We have the predicate p of x such that x greater than 0. Okay, and these are the domain, and we are going to find out in each of this specific domain whether this statement is true or false. All right, so this domain says that list of all integer. So list of all integer means all integers, say -3, like dot 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 -3, -2, -1, 0, 1, 2, 3. Okay, so these are the all values. I mean example of all values. We have more other values also in this domain. All positive numbers, all numbers including positive and integer, including negative integer. So from that list of value, if we find one value of x for which our p of x is true, that means this statement is true. Now you do not need to try all of this, test all of this. So you can see that here if I just use this value p of 1, p of 1 is true. Okay, p of 2 is also true, 3 is also true, but here we found one value, okay, for which our predicate is true. All right, so we can say that for this domain our statement is true. Now list of all positive integers, so 1, 2, 3, like all positive integer. So just try the first one. So first try the first one. You can see that P of 1 is true, so this one is true. So what about this one? All negative integers. So let's see all numbers minus 4, minus 3, minus 2, minus 1. Okay, so if the numbers are negative, we know that a negative number cannot be greater than 0. So it means that there doesn't exist a single value, okay, there doesn't exist a single value for which we can say that P of x is true. Okay, our propositional function or our predicate logic is true. So this statement here is false. It says that we do not have any value for which P of x is true. Okay, now we are saying that our predicate logic, we are making our predicate logic a statement using a quantifier. So we can here we have the example of two quantifier, universal quantifier or existential quantifier, but we have to have also a domain. Okay, so this statement will become this will become a statement, and they will be evaluated to true or false in a specific domain. So let's just have a idea, like a idea about this universal and existential quantifier. So we read it like that: for all, this is the symbol, all right, and existential, we read it like that: there exist. So universal quantifier, a statement with universal quantifier will become true when Px is true for every x in the domain. Okay, and it will become true if P of x is true for at least one x in the domain. Okay, so it will become false if there is one x for which P of x is false. All right, and existential quantifier become false if P of x is false for every x in the domain. Okay, so it's same as like writing using the AND statement. Okay, so these are all values in our domain: x1, x2, x3, xn. Okay, now if we calculate the P of x1 and P of x2 and P of x3, including all values in our domain, if there is one value which returns false, the whole statement will become false. Okay, but if all of the predicate value is true, this statement will become true. Okay, so there exist works like as a AND OR operation. So we can think about it like x1, x2, they are all the values of in our domain. So if we calculate a OR operation with all of them, all right, so if there exists one true for one of value in our domain, all right, so this statement will return true. Now if all of them are false, that will return false. Okay, so let's do some practice here. Okay, so let px is a predicate where x square greater than 0. Okay, px is a predicate where x square greater than 0, and we have a domain consist of all integer number. Okay, so if it's a integer number, that means we have actually all negative, 0, 1, 2, 3, all positive integer. Okay, so what is the value of each of the statement? So first statement is saying that for all x, P of x is true. It means that for every integer number, okay, positive or negative, for every integer number, x square should be greater than 0. Okay, now if you find one integer number for which you can say that x square is greater than 0 is false, that means our statement is false. Okay, so let's find out with one negative integer, P of 3 is true. Okay, P of 1 is true. What about P of 0? P of 0 will be evaluated to 0 and 0 is not greater than 0, so which is false. Okay, so means for every x, P of x is not true, so the whole statement will be evaluated to false. Okay, so what about this one? So this one is true. Okay, we can see that you just take any other value actually other than 0. For every value other than 0, it will be evaluated to true. So if there exists at least one value for which this is true, means this statement is true. Okay, now let's see this one. So we have, in this example, we have px for which x square less than 0. Okay, so for all x px, so these are our domain. Okay, domain consists of all integer number. So can we find a value for which x square is less than 0? Actually there is no value for which x square is less than 0. Okay, so this one is false. Okay, and what about this one? Okay, so this one is also false because there doesn't exist a single value for which x square is less than 0. All right, alright, so in this example our domain is same. Domain is all integer number. So p of x is x plus 1. Actually we write it like that. P of x is x plus 1 equals to twice x. Okay, alright, so what is the value of the first one? So let's find out. P of 1 is okay, let's find out, just if you find one value for which this predicate is false, that means your statement is false with the universal quantifier. So let's find out P of 2. So 2 plus 1, which is 3. So 3 is not same as 2 times 2. Okay, so that means this is false. So you can just say that that's false. Now there exists an x for which this statement is true. So that means if you find one value for which you can show that x plus 1 equals to twice x, that means this one is true. So let's find out what is the value of p1. So p1 equals to 1 plus 1, which is 2, which is same as 2 times 1. Okay, so for this one, x plus 1 equals to twice x is true. Okay, so we found one value for which this statement is true, this predicate is true. That means this statement with the existential quantifier is true. There exists a value of x in this domain for which x plus 1 equals to twice x. Okay, so let's see another example. X square less than 16. So p of x be such that x square less than 16. Okay, in the domain consists of all integer number. So same domain. All right, so let's find out. Say for minus 3, this is true. For minus 3, 3, this is 2. Minus 2, 2, this is true. So what about minus 4 and 4? Okay, so p of minus 4, p of 4, p of minus 5, p of 5, for this value this statement is false. Okay, so that means this is false. But this is true because we have actually couple of values in our domain of integer. For example, minus 3, 3, minus 2, 2, minus 1, 1, for which our x square will be less than 16. So the existential quantifier, the statement with the existential quantifier is true. Okay,